And yeah, we'll change the position in space, and what may happen then when the interaction appears. Yeah, so yeah, that will be the obstacles, and we can have the collisions. And in fact, we have already two types of the interaction. So first one is intentional. So we want to interact with objects. And the second one is non-intentional. When we don't want to interact with an object, but we do, and we need to react somehow to that. Of course, intentional, there will be, you can have picking, but you can have also other tasks like assembly or processing of the elements, yes, like machining. All the types of what we do with the object intentionally, it can be there. But also we need to remember that there is the other side when we interact with the objects non-intentionally. So we don't want this interaction, and the interaction appears. Okay, so what are the characteristics of the interactions? In fact, we said intentional or non-intentional. We either are interested in the position, we can be also interested with applying certain force to the objects or not applying a certain force. In the intentional interaction, we may say, especially in machining, but also in picking tasks, you may want, let's say, to grasp an object with a certain force, or you need to apply a certain torque to the objects that you are processing. On the other hand, when you have a non-intentional interaction, for example, with a human, so you are driving a mobile robot and you collide with a human, to be safe, the robot needs to satisfy certain norms, and these norms say what is the maximum force that the robot can interact with a person to be allowed to be in the same area as people. So we can either want to apply certain force bigger than or force smaller than, depending on the kind of the interaction and the applications that we have. Okay, so when we need to introduce force to robot control, yes, in any case when this force is needed either to make a task or to finish the task, or to interact, or to not interact too strongly with the people. Before we go further, I would like to show you some examples so we can see how it looks like in practice for different types of the robots. So firstly, the example of non-intentional interaction, that's the example of the so-called passive force, passive force control, when after the collision, the robot, as you can see, reacts to that and to not destroy the gripper. We can also look at that kind of the passive compliance, so-called passive compliance in the grippers. We already were showing that kind of the grippers that you move the gripper hand here at the bottom, but what you get is the elasticity in the elements of the grippers. They just make closing the grasp. We are already showing that and at the lecture about the grippers, but that's just to recall, that's also an element of the force control. We will be also saying about the active force control, and this example you will see in the assembly task, and this the assembly task in here, and as you will be able to see, when the when the robot places the button in the box, it in fact applies certain type of the force. There is also a force control when you try to rotate this screw, as you also need to ensure certain value of the torque, which is a form of the force control as well. And especially here, you can see that the robot controls the force. It's not only a positional control, but it's also changing the registering and modifying the movement depending on the force that appear. Okay, that may seem a bit simple task. We can also show a bit more complex. That's the example of the shank assembly. When you that's again an example of the assembly task. And because of the error of the measurements, you can see that it's a very long element to be put here. So you need to, usually because of the positioning error, you cannot really rely on the position control. You need to apply to the force and see in what direction the force appears and react to that, changing the movement of the robot. Okay, so those are the ideas of the industrial applications. We can also look at the options of steering the robot or teaching a robot using the so-called human leading. So that also uses the robot here measures the forces that are applied, and it uses active compliant control just to modify its position to reduce the force applied by the person. So in fact, moving in the direction the person wants to move the end effect. And one of the examples that some of you already seen, the robot that we have in laboratory that also has this option. So if someone wants to see and experience how it works, you can do it in the 010 laboratory to see of how it is different from the standard, how compliant robots are different from the industrial robots that we can work with. Okay, so that's just a brief overview of the videos of how it looks like. So you can so you know of what we are talking about. So let's say about the some rules and the theory that is behind that. So as we said, practical industrial applications that we have, like polishing, where you need to apply certain force, machining, again, assembly, that you need to react to certain movement, like this shaft insertion example, then task teaching, and in service robotics, human-robot interaction and safety. So observing the forces and reacting not to apply too much force to the people. Okay, as I said, so we need to go a bit into the theory. That's something that you already know. So we have the Jacobian matrix, the Jacobian that represents the transmission of the forces of the velocities between the velocities in joints and the velocity in the task space, and that's the Jacobian that is the formula that allows us to transform the velocities from one space to another. And when we can of course split the Jacobian into two parts, one part related to the linear velocities, in the second part related to the angular velocities of the robot or end effector in the task space. And again, something you had on the introduction to robotics, that is the statics, and the statics that was saying about the forces and torques, how they can be, because we can transfer or transform not only the velocities from the task space to the joint space, but also the forces. And we can do it either in dynamics, in the dynamic movement, but we start usually with statics. So when we think about the not moving situations, when we have only a static force in a fixed position of the robot. So we are in the equilibrium state, then we can use the virtual work principle, and this virtual work principle will say that our external that our torques in the joints are related with the external forces that are applied to the robot with the transposed Jacobian. Okay, so just to have a simple example of how it works, you can find the simple two joint manipulator. We have one translation, one rotation, and when we calculate the kinematics and the Jacobian, that's nothing really special. We will get this formula for the statics that says of how the x and y forces influence the torques applied to the joints. So if we don't have external forces, we don't have external additional torques in the manipulator. But if we, let's say add and say, okay, so what happens when we put here an object and when the